Okay, so with this video, we're going to basically just do two examples of Newton's second law for rotation. There's really not a lot to teach about using the second law. You really just have to do a few sample problems and just do some practice. So I want you to take a moment and see if you can figure this one out on your own. It's not a particularly challenging problem, and there's just a couple of things I want to point out real quick. One, I just want to remind you that the second law for rotation is tau net is equal to I alpha. And then the other thing I want to point out is that a flywheel is nothing more than a heavy disk. Usually it's a disk. That's the typical geometry, but that's all a flywheel is. It's just a big heavy disk. So go ahead, take a moment, and see what you come up with. Okay, so let's take a look at what's going on here. This is a solid disk through and through from one side to the other, and this gray spot just represents the pulley that's being referenced up here. I should say it's implied that there's a pulley, but the string is attached to the disk a distance of 6 centimeters. It's a distance of 6 centimeters from the center of the pulley. So that means right here is going to be the center of our disk, and the string is coming off right here. So the string points in that direction. Okay, now one of the things that I'd like to point out to you is that anytime you have a string coming off of a disc or a pulley or something like that, it always comes off at a 90-degree angle. Okay, so this is always going to be 90 degrees. Doesn't matter what the orientation of the string is. If it's pointing like this, up and to the right, instead of just straight right, it's still going to be 90 degrees to that. So that's a useful piece of information. Okay, so the string is wrapped around this pulley, and we're just going to be pulling on that string with a constant force of 10 newtons. All right, so let's go ahead and get started now that we have the basics of what's going on in the problem. In part A, we have tau net is equal to I alpha, and we only have one force, so we only have one torque, and so we're going to say that the torque is going to be R times F is equal to I for a solid disk is going to be m r squared times alpha. Now notice that this R and this R are two different R's. They are not the same thing. Okay, so we want to distinguish between those, and in fact I will even make sure I label our circles so that we realize and understand that that is R, capital R. It's the radius of the disk itself. Little r is the radius of the small pulley, the small massless pulley that the string is tied to. Okay, so solving for alpha, we're going to get, forgot my 1/2 here. So solving for alpha, we get 2r times f over mr squared. So alpha becomes 2 times 0.06 times 10 newtons divided by the mass of the disk, which is 1, and the radius of the disk is going to be not 30 centimeters but 15 centimeters. So that's 0.15 meters, and that quantity is going to be squared. So the angular acceleration is going to be 2 times 0.06 times 10 divided by 0.15 squared. And we're going to get 53.3 radians per second squared. Okay, so that's the answer to part A. Now, part B, we're being tasked with determining how many rotations this flywheel is going to make in a 10-second period of time. Well, this is a kinematics problem, and now we have the angular acceleration, so let's list out our data. We have delta theta is equal to Well, that's what we're looking for. And then we have omega initial was 0. Omega final is an unknown quantity. Alpha, we just calculated, was 53.3 radians per second squared. And then finally, time is going to be 10 seconds. So the equation which is going to most readily fit this data would be our position function for rotation. So we have delta theta is equal to omega initial t plus 1/2 alpha t squared. Omega initial was 0, and so delta theta becomes 1/2 times 53.3 squared, 53.3 times 10 squared, which is 100. So let's do the math very quickly. Basically, we have 53.3 times 50. So this becomes 53.3 times 50, and we get 2665 for delta theta. Now, what are the units of delta theta as they currently stand? You should have said radians, and the problem is asking for rotations. So we have to convert 2665 radians into rotations, and so we have one rotation is equal to 2 pi radians. So our radians cancel, and so we just have to do 2665 divided by 2 pi. Now, you'll notice that I did the 2665 divided by 2 divided by pi. A common mistake that students make is going to be this in their calculator. They'll do 2665 divided by 2 pi. But the problem is what you've done mathematically, because there's no parenthesis in here, mathematically what you've done is you've said 2665 divided by 2 times pi, and that's going to give you an incorrect answer. So make sure you're using enough parentheses to make sure that the order of operations works out the way you're intending them to work out. All right, so our answer is 424 rotations. So ultimately, delta theta is equal to 424 rotations. So let's go ahead and take a look at a second example. Okay, so here's our second example. Take a minute and try this one on your own. It's definitely a little bit trickier because of the information which was given, but let's see what you come up with. Okay, so welcome back, and let's get started on the problem. So we have a disk. Just draw a picture here so we have a visual reminder of what's going on. It has a mass of 0.2 kilograms and a diameter of 4 inches, so the radius is 2 inches. And 2 inches is approximately 5 centimeters because it's going to be 2 times 2.54. So we're going to say that our radius is going to be equal to 5.08 centimeters, which becomes 0.0508 meters. Now, this 5,000 RPMs is omega. It's just not in radians per second, so we're going to have to convert this. So omega initial, just writing out our information, omega initial is equal to 0 because it starts from rest. Omega final is equal to 5,000 revolutions per minute. And so now we're going to have to convert revolutions per minute into radians per second. So to do that, we're going to write it out. We have 5,000 revolutions per minute times 2 pi radians per revolution times 1 minute is equal to 60 seconds. And so we're going to get 5,000 times 2 pi divided by 60. And we get 524 radians per second. So omega final is going to be 524 radians per second. And we're given a time interval of 0.85 seconds. All right, so we're being asked about the torque. And since we're being asked about torque, we're just going to start with Newton's second law, because if we were to just use our definition of torque, we have torque is equal to R times F times the sine of phi. The problem is we don't have the size of the force, we don't know where that force is applied, and so using our definition of torque is useless in that context. It's not used for problem solving, it's just used for defining. So to get our torque, we're going to use Newton's second law for rotation, and we're going to say tau net is equal to I alpha. Now a grinding disc, that's basically a solid wheel, or a solid disc, so that's going to be 1/2 mr squared. Alpha is ultimately what we're going to have to find because we're looking for the net torque. So tau net is equal to 1/2 the mass of the disk times the radius of the disk squared times alpha. Now to get alpha, we're going to have to go to kinematics. And we're given time, omega initial, and omega final, so it would stand to reason that we would use alpha is equal to delta omega over delta t, or alpha is equal to omega final minus omega initial divided by t, where omega initial was 0. So we get tau net is equal to 1/2 mr squared times omega final over t, and that's what represents alpha. So now let's put in our values. So we get tau net is equal to 1/2 times the mass of our disk is 0.20 kilograms. The radius we said was 0.0508 meters. That'll be squared. Omega final was 524 radians per second, and that would be divided by the 0.85 seconds. So let's calculate this. We have 0.5 times 0.2 times 0.0508 squared times 524 divided by 0.85. And that's going to give us 0.159 meter newtons. So tau net is equal to 0.159 meter newtons.